So these 16 wires are used by 8085 microprocessor to transfer both data and address. In this lecture, we are going to talk how the microprocessor is going to use them to address and how many different combinations and memory cells the microprocessor could address. So if you have 16 wires, every wire could have either the low voltage value, which we call 0, or the high voltage level, which we call 1. So these 16 wires could have the values of 16 zeros to 16 ones. We want to see how many different combinations these could be. If I write different combinations, the first one would be 16 zeros, right? So I say this is the value 0 in the decimal numbering system. Our numbering system is decimal. You should already be familiar with this, but decimal numbering system uses 10 digits from 0 and 9. 10 is bigger than 2 to the power of 3 and less than 2 to the power of 4. 2 is the number of digits used in binary because every wire could have one of the two values. In hexadecimal value, another numbering system, we use 16 digits from 0 to 9 and also A to F. So in decimal, after 9, which is the biggest value in the decimal system, after the 9, we need to use 2 digits, 10, 11, 12, 13, 14, and so on. But in hexadecimal, after 9, we use A as the value of 10. B, C, D, E, and F. F would be equivalent to 15 in the decimal. So we use 16 different digits, and 16 is equal to 2 to the power of 4. As we see, the number of digits in hexadecimal is an integer multiple of the 2, which just tells us that using one digit in hexadecimal, we could just create all the different combinations for 4 different digits in the binary or 4 bits. So here I say 16 zeros is equal to 0 in both decimal and hexadecimal, and this would go on until 9 in both of them. Then we have this value, which would be 12 zeros and 1010, which is 10 in decimal or A in hex. And also we just go on until we get the final combination of the first 4 bits, which would be 4 ones. 4 ones in the decimal is equal to 15, and in hex is equal to 15. So as we promised, all the different combinations of the first 4 bits have been resolved using one hexadecimal digit from 0 to F. After this, we need to use 2 hexadecimal digits. So because of this fact that it is an integer multiple of 2, we could say that for every 4 digits or for every bit in binary, we use one hexadecimal digit. If you have 16 digit in binary, this is just for simplicity. You see, working with 0 and 1s is a bit hard, and because in decimal 10 is not an integer multiple of 2, so the hex would be the best one. So if I have 16 bits here, I would use 4 hexadecimal digit to just represent all the different combinations. So as you see, this would be 0, this would be 0, 0, and this would be 0. So we have 4 zeros in hex, which would be equal to 16 zeros in binary. Then 0, 0, 0, 1. Then up to here, which would be 0, 0, 0, and F. I mean, like this one. 3 zeros and F. And the next combination, so this should be 1. The next one would be 0, 0, 1, 0, as you see here. And also all the different combination. As an example, this would be 0, 0, 1, and this is 8 plus 1, which is 9. So 2 zeros, 19 is equivalent to this value in the binary, or 25 in decimal. And we could just draw all the different states. This would be, as an example, again, 0, 0, 1, F, which is equal to 31 in the decimal. And the last combination, you see, in the decimal, we are just using different combinations for different states. This is the first digit, and then we use 2 digits, and here would be the last value, which is the 65,535, equivalent to 16 different ones. This in the hexadecimal, this would be equal to F, 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 and F. So these are all equivalent in different numbering system. So using 16 wires, which is all the wires that 8085 microprocessor is using for addressing different kind of memory. We could have all the different combinations from 16 zeros to 16 ones, which is from 0 to 65,535 in decimal, giving us 65,536 different combinations, or we call this just 64K. Well, 64K in the computer is not 64,000. It is 64 times 1K. This is 1024, which would be equal to 65,536. And this, as you see in the hexadecimal, would be from 4 zeros to 4 Fs. So what we are saying is that this microprocessor, since it is using 16 wires, it could address the values from 4 zeros to 4 Fs or 64K. We say the address space of the 8085 microprocessor is equal to 64K. Now, considering that every memory cell would have 8 bits of data or 1 byte, we would say that the address space of the 8085 microprocessor is equal to 64 kilobytes. So to just simplify it further and to completely understand different ranges in this address space, this is the whole memory that the 8085 microprocessor could address because of the limitation of number of wires used for addressing. So for simplifying it further, you want to just draw all the different ranges in this address space. I say from 0 to 4095 would be the first 4K. You see 4K would be equal to 4 times 1024, right? This is 4096. So it would be from 0 to 4095. This is the first 4K in our 64K range. Then I just add the 4096 to this value to get the next range, which is 8195. This is the second 4K. And again, adding this to 4096, we would get this value, and this would go on until we get the last value, which is 65,535. But in hexadecimal, if you look, we say the first range is from 0 to 0FFF is the first 4 kilobytes. Then from 0FFF to 1FFF would be the second 4 kilobytes. And from 1FFF to 2FFF would be the third 4 kilobytes. And well, we would have 16 ranges of 4 kilobytes forming our 64 kilobytes of address space, or all the memory that 8085 microprocessor could address. So as another example, let's say that what this value is. 7FFF in binary would be equal to 0111, and then these number of ones, every F is equal to 4 ones, right? Then the next range would be 8FFF, so 1000, and then the rest should be 1. As an exercise, just prove all these values that to just be more comfortable with binary and converting them to decimal and hexadecimal. As I said, you needed to know this already. The goal of this lecture was to just tell you the concept or the abstraction of address space, what the address space is. Why is it that we say 8085 microprocessor cannot address more than 64 kilobytes of RAM? The reason was because it uses 16 wires to address different memory, and 16 wires we could only address to the power of 16, right? So just prove that the difference between these two would be equal to actually 4 kilobytes. And well, finally, well, I think that's it. So in the next lecture, we are going to learn how we could just interface different kind of memories to different locations in here. I know usually people say that interfacing should be the last part taught in the different microprocessor like 8085, but I think it would be a better thing to just right now tell you, just imagine we have only 2 4 kilobytes of memory and we want to map them to here and here. It's just to understand this other kind of abstractions, like what does it mean that we say we map 4 kilobytes of RAM to a specific place in our address space. So see you in the next lecture.